In chapter 6.1, we look at the shapes of different molecules. You'll see I've written out here, the shape of a molecule is determined by the arrangement of electron pairs around the central atom. To know how electron pairs are arranged around the central atom, you're going to need to draw a dot-cross diagram. So if I look at my first example, BF3, I know boron is in group 3, therefore it's got 3 outer electrons, and it is forming 3 bonds with 3 fluorine atoms. Each of those bonds must have 2 electrons, one from boron and one from fluorine. Boron only has 3 outer electrons, and I've drawn my 3 dots already. Fluorine has 7 outer electrons, so I have another 6 crosses to draw on each fluorine atom. When I'm predicting the shape, I'm not looking at fluorine. I'm only looking at the central atom, and the central atom is boron. Around boron, I have got 1, 2, 3 pairs of electrons. When I'm talking about pairs of electrons, there's 2 different types of pairs you can have. You can have a bonding pair. By bonding pair, you should have 1 electron from one atom and 1 electron from another atom. So this would be a bond pair, this would be a bond pair, and this dot cross would be a bond pair. The other type of electron pair you can have is a lone pair. Boron does not have any lone pairs, but you can see fluorine has 1, 2, 3 lone pairs. This fluorine also has 1, 2, 3 lone pairs. So there's 2 different types of electron pairs. Bond pairs, so the pair of electrons involved in a bond, and lone pair, a pair of electrons that just sits on the atom and is not involved in the bond. Boron has 3 bond pairs of electrons. So I'm going to write bond pairs of electrons, And we know that electrons are negatively charged, and we know that electrons, because they're negatively charged, they will repel each other. This means that the bond pairs of electrons around boron want to be as far from each other as possible. In order to be as far from each other as possible, they will take on the following shape. And we call this shape trigonal planar. The bond angle between the different bonds, so between the boron-fluorine bond, between these 2 boron-fluorine bonds, the angle is 120 degrees. The angle between these 2 bonds is 120. The angle between these 2 bonds is 120 degrees. So they'll take up position as far away from each other as they possibly can, because pairs of electrons will repel each other because they are all negatively charged. So this is the shape that BF3 will take. It's trigonal planar with an angle of 120 degrees between each of the bonds. If we look at NH3, I'm going to draw out nitrogen. So nitrogen has got 3 hydrogens, and the dot cross diagram will look like this. So nitrogen is forming 3 bonds. That uses up 3 of nitrogen's electrons, but it's got 5 electrons in total because it's in group 5, so it's got 2 electrons that are not bonding, that are on as a lone pair. Hydrogen only has 1 electron each, so I've drawn in all of the hydrogen electrons already. So when I look at nitrogen, that's my central atom. I've got 1, 2, 3 bond pairs. But I also have 1 lone pair. Now, to look at the formula BF3 and NH3, you might think that they're going to have the same shape, but when you actually draw the dot cross diagram, you see that BF3, there are only 3 bond pairs around the central atom, but in NH3, you've got 3 bond pairs and 1 lone pair. So the arrangement of electrons around the central atom is different, and that is going to affect the shape. We've got 3 bond pairs and you've got 1 lone pair. So you've basically got 4 electron pairs sitting around this nitrogen atom instead of just 3. Each of those electron pairs are going to repel each other, and they want to be as far from each other as possible. A lone pair of electrons can repel more than a bond pair does. So a lone pair is even more repulsive than bond pairs and will push those bond pairs even further away. This means that that the ammonia molecule actually has quite a different shape than the BF3 molecule because of that lone pair. And this shape here, we call not trigonal planar, we call trigonal pyramidal. And instead of having this 120-degree bond angle, you've actually got a bond angle of 107 degrees. And the reason that angle is so much smaller is because you've got a lone pair, which will repel the bond pairs as far away from it as possible. So you get a much smaller bond angle and you end up with a different shape. So we've got trigonal planar and we've got trigonal pyramidal. We have a bond angle of 120 and we have a bond angle of 107. If we look at another example, we're going to look at CH4. So I've got carbon and I have got 4 hydrogens around it. Carbon has got 4 electrons in its outer shell and it will use all of those electrons to form bonds. So when I draw out CH4, I see that carbon has 1, 2, 3, 4 bond pairs of electrons. There are no lone pairs of electrons on carbon. All of its electrons are already involved in the bonding. If it's got 4 bond pairs of electrons, again, those pairs of electrons are going to repel each other. They will be as far from each other as possible. So you might think that the way I've drawn it, that those hydrogens are as far from each other as possible, and you would have a bond angle of 90 degrees. We have to remember that these are not 2D molecules. These are actually 3D molecules. And when I draw out methane, it is a 3D molecule. And if you take up the full 3D space, you can actually get a bond angle of 109 degrees, not just 90 degrees. We call this shape tetrahedral. And you'll notice that when I drew it, I drew 2 lines that were just straight lines, and then I drew a wedge and I drew a dash. The 2 lines that are straight represent that those 2 carbon-hydrogen bonds are in the same plane as the paper, so they're just lying flat on the paper. This wedge tells me that this hydrogen is protruding out of the plane of the paper, and this dash line tells me that that carbon-hydrogen bond is going back into the plane of the paper. So this is not just a 2D molecule, this is a 3D molecule. Those electron pairs position themselves as far from each other as possible. You get a tetrahedral shape with a bond angle of 109. If we look over here, we're going to do H2O. Okay, so if I draw oxygen as my central atom, I'll draw hydrogen on each side. So oxygen is forming 2 bonds, 1 with each hydrogen, but it's got 6 electrons in total, so it still has 2 lone pairs. I've already drawn all of hydrogen's electrons. So in this case, around oxygen, because we're only looking at the central atom, I've got 2 bond pairs, 1 and 2, and I've got 2 lone pairs. So I've got 2 bond pairs, and I've got 2 lone pairs. The way I've drawn at the moment, those hydrogens are as far away from each other as possible, okay? But we have to remember that you've also got lone pairs, and those lone pairs of electrons will also repel. And the lone pairs of electrons will repel more strongly than the bond pairs of electrons. And the actual shape that water takes on, okay, is this. Those lone pairs will repel the bond pairs more strongly. And instead of having a linear shape at 180 degrees, you end up with what we call a bent or non-linear shape with a bond angle of 104.5 degrees. Okay, so for each of these, and you will just literally need to learn this off by heart. If you've got 3 bond pairs of electrons, you've got trigonal planar shape 120 degrees. If you've got 3 bond pairs in a lone pair, it will always be trigonal pyramidal 107. 4 bond pairs, tetrahedral 109. 2 bond pairs, 2 lone pairs, bent 104.5. You literally need to learn those shapes and those angles off by heart. You need to be able to draw your dot cross diagram. You count the number of bond pairs and lone pairs around the central atom, only the central atom. And then if you learn off your shapes and your angles off by heart, then you'll be able to count your bond pairs, count your lone pairs, and write down the shape and write down the bond angle. You need to know those 4. This is the last one you need to know, SF6. So I've already drawn this out for you, okay? Around sulfur, that's my central atom. I've got 1, 2, 3, 4, 5, 6 bond pairs. I have got no lone pairs, so 6 bond pairs. And there are no lone pairs at all. If you've got 6 bond pairs, it takes on an octahedral shape. Again, this is not a 2D molecule. All of these fluorines and sulfurs don't all exist in the same plane. Some will be pointing forward, some will be pointing back, and you end up with a bond angle of 90 degrees. So 6 bond pairs is octahedral, gives you 90-degree bond angle. Okay, I have gone through all of these shapes on page 2 of the chapter 6 booklet. Okay, you need to learn the shapes, you need to learn the bond angles, and then it's just a matter of drawing the diagram, counting the bond pairs and the lone pairs around the central atom, and then using that to predict the shapes. Okay, remember, lone pairs do repel more than bond pairs, which is why something like water takes on this bent shape with the bonds slightly closer to each other than you would have expected initially. On page 3 is exercise 1. In the next video, I'm going to go through the answers to exercise 1. So I'd advise doing exercise 1 for yourself and then checking the next video for the answers.